Welcome to our first lesson on logic. We will be looking at different kinds of reasoning, and in this case we are mostly going to work on inductive reasoning. We'll look at the deductive reasoning a little bit later. We will also look at this idea of a counterexample, which will help us disprove different statements, as well as a way of writing statements in a conditional form and notation for these statements. Okay, inductive reasoning, what is that? Inductive reasoning occurs when we observe a pattern and we apply a rule. We come up with some rule based on this pattern that we see, and humans are really wired for this kind of thinking. We can't help it. Once we come up with some sort of rule, we call this rule a conjecture. So for example, if I notice when I get up in the morning, the sun comes up, I may make a conjecture that says every morning the sun's going to come up. So what's the problem with inductive reasoning? Well, I hope that my conjecture of every morning the sun will come up is a true statement. But do I know that for sure? In inductive reasoning, you have to know that every example, every possibility is exhausted to know that if it's true. So a better example might be if an animal has 4 legs, then it is a dog. And if that's my experience, if I've only ever seen dogs and I've never seen any other 4-legged animal, that's true to me. But then one day, if I see a cat, my conjecture is not true. So a problem with inductive reasoning is that unless you can prove it's true for every possibility, every possible thing that can make that condition true, I don't know if it's true. So we call this disproving of a conjecture. We find a counterexample. So the counterexample is the thing that says it's not true. So when my example is 4-legged creatures are dogs, a cat, it would be a counterexample. So I've got some other ones as well. So let me see if I can get that to come up. Okay, so here is a conjecture I'm making based on observation. So I go to school every Monday through Friday. It seems like I do that. Well, is there a counterexample to that? Well, maybe today is President's Day. It is Monday, but it's also President's Day and we don't have school. So I found a counterexample, so false, right? I found a counterexample. Whoops, pen ran out there. Maybe it's President's Day. Let's see. All prime numbers are odd. So this conjecture, first of all, you have to know what prime numbers are, and you have to know what it means for a number to be odd. Prime numbers are numbers, integers, greater than 1, whose factors, its only factors, are 1 in itself. Odd numbers are numbers that, if you divide by 2, you get a remainder. So numbers like 1, 3, 5, 7, 9. And prime numbers are numbers that only have 1 in itself as factors. So if I take 5, does 5 only have 1 and 5 as its only factors? And it does, and 5 is odd. So there's an example that makes it true, that works. 7 works. 9? Well, 9 is not a prime number. So since this condition isn't made true, I cannot look at the result. So that doesn't fit in with my model, with my observation. So I guess this must be true. Well, is it? What about the prime number 2? 2 is a prime number. It only has 1 and 2 as its factors, but 2 is not an odd number. So I found a counterexample. So I only need to find one counterexample to disprove a conjecture. There may be more. Up here, I go to school every Monday through Friday. Maybe it's the summer and I don't go to school. So there can be more than one counterexample, but I only need to find one to disprove it. We're going to look at a way of taking these conjectures and writing them in a certain way called a conditional statement that may help us a little bit in proving or disproving our statements. So we're going to use an if-then format. So if a condition is true, then we have a conclusion. Something occurs. So here's my example. If an animal meows, we call that our hypothesis. This is the condition that must be true for our conclusion to occur. So if an animal meows, then it is a cat. Now we can argue whether our hypothesis is true or not. For the sake of example, in this particular presentation, we're always going to assume here that this hypothesis is true. So if this is true, then that's your conclusion. If something, then something. Okay, so we're writing our conjectures as conditional statements. So we can also use mathematical notation. So what we do is we say, all right, let's call this thing, that hypothesis, P. And I can choose any letter I like. I'm choosing P here, and I'm going to use another letter, Q, for my conclusion. So another way to write all these words is to say P using an arrow, Q. And we read that P implies Q. It's just a shorthand instead of writing out all these words because too much work. And here we've got a little bit of more of a mathematical way of presenting a logical statement. So looking at different forms of conditional statements, if this is my initial statement, and again I'm going to call this thing P, and I'm going to call this thing Q. So this statement is P implies Q. I can create the converse of this statement, a converse, and a converse is when you swap the hypothesis and conclusion. So I can write that as Q implies P. So what does that mean? That says if an animal is a cat, then it meows. Converse, you swap your hypothesis and conclusion. We can also take the inverse of a conditional statement. An inverse is when you take this initial statement, my P implies Q, and I negate or make a negative out of each of them. So if an animal doesn't meow, then it is not a cat. And the way we write this in notation is we say not P implies not Q. You may see certain textbooks or online notations, instead of this little squiggle, which means not, they'll use a symbol like this, a little bar there. That's okay too, but it's basically saying if not this, then not that. If it's not a meowing animal, then it is not a cat. And we also have a contrapositive of a statement, and a contrapositive combines both of these. You take the initial statement and you take its converse and its inverse to get not Q implies not P. So this statement becomes if it is not a cat, then it doesn't meow. Okay, so we have our converse, swap the two, we have our inverse, negate them, and we have our contrapositive, which does both things. We can talk a little bit about equivalent statements. That's probably appropriate here. We assign truth values to a statement. So in our examples here, I'm always going to assume that this statement is true, and then I can examine, is my converse true? Is it true if an animal is a cat, then it meows? Generally speaking, that is true. You could be very picky and say, well, you can find an instance of a cat that doesn't meow, in which case you would say this is false. For the sake of this argument, generally speaking, cats do meow, so if an animal is a cat, then it meows. What about the inverse then? If it is an animal that does not meow, then it is not a cat. And generally speaking, that is true too. Again, you can find individual counterexamples, but for the sake of our example here, I'm going to say that's true. Now, a contrapositive, not Q implies not P. If this is a true statement, if an animal meows, then it is a cat. If it is not a cat, then it does not meow, will also be true. So in this case, all my statements appear to be true. Let's do one that maybe it might be a little bit more obvious if it's true or not. So how about this? If it rains, then I carry an umbrella. So this is going to be like the P. That's my hypothesis. And I carry an umbrella is like a Q. So if I look here, and let's say, I'm going to assume this is true. If it's not true, then we don't need to look at all the other statements. So the converse, Q implies P. If I carry an umbrella, then it rains. Now, is that true? If I carry an umbrella, then it must be raining. Well, what if it's very, very sunny and I'm carrying an umbrella because I don't want too much sun on myself? So in this case, the converse is going to be false. Let's think about the inverse. Not P implies not Q. So if it doesn't rain, then I don't carry an umbrella. Well, think about this. It's very similar to saying the converse here. If it's not raining, then I'm not carrying an umbrella. Well, maybe I am carrying that umbrella because it's too sunny. That's false. And think of the contrapositive now. That's the not Q implies not P. Oops. If I'm not carrying an umbrella, then it's not raining. If I'm not carrying an umbrella, then it's not raining. So that one will be true. And it turns out that your original statement and contrapositive are always equivalent. They will have the same truth value. And your converse and inverse also are equivalent statements, and they will also have the same truth value. And sometimes you have to think about these a little bit, but these are the what we know logic tells us is true or not about equivalent statements. Biconditional statements. What's that? If you have a statement where the initial statement and the converse are both true, you have what's called a biconditional statement. And we use the words if and only if, abbreviated IFF, to connect the two clauses. Looking at this example, if a polygon has 3 sides, then it is a triangle. To determine if it's biconditional, you have to look at its converse. So first, let's see what we've got here. So I'm going to call a polygon has 3 sides, my hypothesis, right? I'm going to call that P, and I'm going to call my conclusion Q. So we have here P implies Q. So to look at the converse, you take Q implies P. So let's see if it works. If a polygon is a triangle, then it has 3 sides. Yes, true. So I have a true converse to go with my true initial statement. So I actually have a biconditional. So to change this in words, I cross out the if, I cross out the then, I replace the then with if and only if, and now my statement reads, whoops, that did not come out so well. A polygon has 3 sides if and only if it is a triangle. And that is a way of saying both the initial statement and the converse at the same time. Now the notation, all you do is instead of using the single arrow, you use a double arrow. So P if and only if Q lets me know that P implies Q and Q implies P, both at the same time. Let's look at another example here. If a quadrilateral is a square, then it has 4 equal sides and its angles are 90 degrees. All right, so here is my hypothesis and here is my conclusion. I'm going to use different letters here just to show you that I can. I'm going to call my hypothesis S. So S is the quadrilateral is a square. Now there are actually 2 things that are going on here in my conclusion. I've got 4 equal sides here. I'm going to call that T. And I also have that the angles are 90 degrees. I'll call that R. Well, that's an R. I've got this word and here though. So I'm going to use a symbol for and. It looks a bit like a circumflex. That is our logic notation for and. So to write my initial statement, I would write S implies T and R. To determine if it is biconditional, I need to look at the converse. So I swap the hypothesis and the conclusion. Let's see. If quadrilateral has 4 equal sides and its angles are 90, then it is a square. True. That is true too. So this is biconditional. So I'm going to take my initial statement here and I'm just going to make a double arrow. And that's how I would write the notation. Again, with the words, all you do is you cross out the if, you cross out the then, you put in an if and only if. Quadrilateral is a square if and only if it has 4 equal sides and its angles are 90. And there's my notation over here. One more example here. I was trying to take our previous example and maybe make it a little more thorough, more precise, so it can be true. If I use an umbrella, then it is either rainy or sunny. Here is my hypothesis. I'll go back to P. And then here is my conclusion. Now once again, I've got kind of two things going on here, rainy or sunny. So for the rainy, I'll call that Q, and for the sunny, I'll call that R. Now we do have a symbol that we can use for the word or, and it looks like a V. So my initial statement in notation is P implies Q or R. One or the other is true. So let's now look at the converse to determine if it's biconditional. So Q or R implies P. If it is either rainy or sunny, then I use an umbrella. In this case, I'm going to say, yeah, that's true. So to make this a biconditional statement, I make this a double arrow here. And now my notation is P if and only if Q or R implies both directions of that arrow. In the words, again, you cross out the if, you cross out the then, and replace the then with if and only if. So let's just kind of review some of our notation here. The letters represent the different clauses in your statement. The arrow is our word for, or symbol for the word implies. A double arrow is for if and only if. A shape like this looks like a circumflex is and the V shape is our symbol for R, or. So we've looked at inductive reasoning, which is making a conjecture or a rule based on an observation. We've looked at how to disprove statements created through inductive reasoning by finding at least one counterexample that proves it false. And we also looked at ways of writing our conjectures using if-then statements, our conditional statements. If a condition is true, then we have a conclusion. And we also looked at notation for writing these conditional statements so in a mathematical way. And you just made it through your first logic unit. If you have more questions, please check out the class video on all this. These are all on my website, and you'll get more examples and more explanation.